Hi, in the previous video, we talked about the idea of using the frequency domain to separate the signal and the noise and to remove noise. And we said, okay, even though theoretically we know how to do that, how are we going to do that practically? Okay, how are we going to build circuits that actually allow certain frequencies to pass through the circuits and certain frequencies to cut off? Okay, and let's look at a very simple circuit which does that. Now this circuit, I'm sure you're already familiar with it from the studies that you did in term 1. So so you have R and you have C. So this is a very simple frequency filter, and the basic reason why this acts as a frequency filter is because this capacitor here, C, a capacitor is a frequency dependent resistor, right? So think about this. So if you have a capacitor, what is the impedance of a capacitor? The impedance of a capacitor is ZC, which is equal to 1 over j omega c, right? And if omega is 0, that is if the frequency is 0, Zc for omega tending to 0, Zc tends to infinity, isn't it? If omega starts to become infinity, what does Zc become? Zc becomes 0. So you can see that the capacitor actually acts like a frequency dependent resistor. That is, depending on the frequency of the signal that you input, the capacitor's resistance or impedance changes. Okay, so that property gives rise to the filtering property of this RC circuit. So let's take a look at that. Let me just delete this and let's. So the impedance of this circuit is ZC, let's say. So what is the voltage output then in terms of V in? So V out is going to be equal to V in times ZC over ZC plus R. And we already know that ZC is given by 1 over j omega c. Therefore, we substitute that here and you get this equation. Okay, and therefore, what you get is, let's say, gain equal to V out over V in becomes 1 over 1 plus j omega RC. Okay, gain is basically the output divided by the input, and of course this gain is a frequency of omega. Okay, as frequencies changes, the gain of the circuit changes. Now let's just try to plot the modulus of the gain. The reason why I'm plotting the absolute value or the modulus of the gain is because the gain here is a complex number, isn't it? So it's got a phase part of it, and it's got a amplitude part of it, or the magnitude part of it. And let's just look at the magnitude for a moment. And if you do that, what do you get? What you get is 1 over square root of 1 plus omega RC square. So that's the magnitude of your gain. Now let's try to plot this gain on axis here. So the x-axis is omega and the y-axis is gain. And let's try to plot this gain. So at omega equal to 0, what's the gain? So this term becomes 0. So you have 1 over 1, which is 1. So the gain becomes 1, right? 1. At a very high frequency, what happens to the gain? At a very high frequency, this term becomes much higher than this 1. So we can ignore this 1 and your gain becomes, let me just write it here. Maybe that would be the best. When omega tends to infinity, your gain tends to 1 over omega RC. So it's kind of an inverse relationship to omega. So what you get then is something like this, right? You get a 1 over x kind of a curve, and in between you get some curve like this. Okay, so that's the kind of characteristic that you get. So what you can see is that the gain of this circuit, which is V out over V in, is high or equal to 1 at very low frequencies. And as the frequency goes higher, the gain reduces. Now, what does that mean? What that means is that if your input is a signal of a low frequency, then your output amplitude will be almost the same as the input amplitude. But if your input frequency is a high frequency, somewhere here, then your output amplitude is much smaller than the input amplitude. Okay? So, can you see how this particular circuit is able to kind of remove the high frequencies? It's not completely removing it, but it's reducing its amplitude while keeping the amplitudes of the low frequency signals at at a certain level, or keeping it the same, right? So here's one of the first frequency filters that you have studied.